how many distinct divisors of 360 are there? That's a good question. There's a lot. Like 1, 2, 3, 4, 5, 6, 8. I'm going to be counting for a while if I try and count them all. We have to be a little more systematic about it. So what we really need to know how many divisors there are of a number, we need to know its prime factorization. So 360 is equal to 2 cubed times 3 squared times 5. Or if you were being, right, if you're actually showing the work, I would be like, it's 36 times 10. 10 is 2 times 5. 36 is 9 times 4. And that's a 3 times 3 times 2 times 2 times 2 times 5. So if I want to count all the different ways I can have a distinct factor, well, I can either have 2 to the 0th power, the first power, the second power, the third power. So there's 4 different choices for what power of 2 I can have. I can have 3 to the 0th, first or second. I can 5 to the 0th of the first. So it looks like I have 4 choices for my power of 2 times 3 choices for my power of 3 times 2 choices for my power of 5. 4 times 3 times 2, that's going to be 24 distinct factors. Kind of neat. It's kind of a lot, which makes sense. I mean, 360 is a number with a lot of factors. And you can apply this logic to any number, or you could go much smaller. So let's say we want to say, let's ask the same question for, what about 20? We could write them all out, right? 1, 2.
Recording in progress.
Oh, okay. Recording, right? Yeah. Scaring me with that. It's all right. So 1, 2, 4, 5, 10, and 20. But you could also do the same sort of thing where the prime factorization of 20 is 4 times 5, which is 2 squared times 5. So you could say, okay, for 2, you could have 2 to the 0th, the first or the second. For 5, you could have 5 to the 0th of the first. So you have 3 times 2, which is 6 choices. There's 6 possible divisors, distinct divisors of 20. If it works here, it definitely works up here. Where did this logic come from? Are these multiples of the number 20? So no, these are factors of the number 20. So these numbers here, 1, 2, 4, 5, 10, and 20 are all of the factors of 20. And so the way we're getting 1 is 2 to the 0 times 5 to the 0. The way we're getting 2 is 2 to the first times 5 to the 0. 4 is 2 to the second times 5 to the 0. 5 is 2 to the 0 times 5 to the first. 10 is 2 to the first times 5 to the first. And 20 is 2 to the second times 5 to the first. So those are all the possible ways you can have a power of 2 that's 0, 1, or 2, and a power of 5 that's 0 or 1. And those constitute all the possible distinct factors of the number 20. I don't want to write them all out, but we could do the same thing for 360. You could have 2 to the 0 times 3 to the 0 times 5 to the 0. And then 2 to the first times 3 to the 0 times 5 to the 0. And then 2 to the second times 3 to the 0 times 5 to the 0. And then 2 to the third, right? It goes on. But these are all the possibilities with, 3 to the 0 and 5 to the 0. And then I could do the same thing with 2 to the 0, 3 to the first, 5 to the 0. Same 4 combinations with just changing the power of 2. And I can do the same thing with 3 to the second. And then I can do all those 12 again with 5 to the first. So there's a lot of different distinct factors of 360. So not all of them will be needed to figure out our choices, like the factor of 10. No. So specifically, if someone asks you about how to find all the distinct factors of a number, what you actually need is the prime factorization. So I didn't stop at 10 because 10 is not a prime number. What I did was I broke 20 down into 2 times 2 times 5. And I broke 360 down to 3 times 3 times 2 times 2 times 2 times 5. So that's all it's all the prime numbers that multiply to make up the number. And then we're just saying, okay, well, I have at most 3 2's multiplied together, but I could have less than that. I could have 2 or 1 or 0. Same thing for the 3's. I could have 2 or 1 or 0. Same thing for the 5's. I could have 1 or 0. That's definitely the logic there. Other questions about this? Kind of an interesting question. I mean, I think all these questions are interesting to some degree because I think counting is interesting, but they might not be that, right? It's a big deal. So there's, what? I didn't actually write most. There's 24 factors of 360. Okay, neat. Let's move on. But other people are like, yeah. Let's look at some other examples. How many even numbers are there between 20,000 and 70,000 with distinct digits? Okay, so I'm just going to give myself some space to work with. There are my 5 digits. Now I want to think about what kind of restrictions I have for each spot. So let's look at the last spot here first. If it's an even number, if this 5-digit number is an even number, that last digit better be what? Even numbers have to end with even numbers. Right? I can't have a 1 there, otherwise it would be odd. Or a 3, or a 5, or a 7, or a 9. The last digit of an even number overall has to be even. It has to be 0, 2, 4, 6, or 8. There's no other option. And our first number, since we're between 20,000 and 70,000, my first number could be 2, 3, 4, 5. Can it be 7? Well, so is there a number between 20,000 and 70,000 where all the digits are distinct? It starts with a 7? No, there's not. And the only number between 20,000 and 70,000 would be 70,000, and that doesn't have distinct digits. Okay, so we've got choices there. And now we have to figure out what's going on with the rest of these. Well, I think we need to break this up into a couple of different cases. So let's say case 1. The first digit is even. So the first digit is 2, 4, or 6. Okay. So if the first digit is 2, 4, or 6, there are how many choices for it? It's not a trick question. This many, right? 3. I'm just right. So why? So actually, I should back up. Why 2, 4, or 6? Why do I care about breaking up into 2, 4, or 6 versus being a 3 or 5? Well, the first digit being even limits the number of choices for the last digit because we said all the digits have to be distinct. So that's why I'm kind of breaking this up into the case where the first digit is one of these even numbers. Excuse me. So we have 3 choices for the first spot. And if we use one of these even numbers, how many choices do I have left for the last spot? Well, 4. Right? There were 5 even numbers to pick from, but I've already used up one of them in the first spot there. Maybe it was 2, maybe it was 4, maybe it was 6. Okay. And then I've used up 2 of the 10 digits that are possible. The rest of the 3, anything goes. So there's 8 choices here, 7 choices here, and 6 choices there. And that's equal to 4,032. But we're not done, right? Because those are all the cases where the first digit is either a 2, a 4, or a 6. You could also have another case where the first digit is a 3 or a 5. Okay, I want you guys to figure out what this is going to look like. How many choices do you have for your first thing? How many choices do you have for your last thing? And how many choices do you have for the rest of them? I'll give you a minute or so to work on that. You guys at home too, work on that. You have 3 or 5 in the first spot. There are how many numbers to pick from there? You have more choices at the end, though. That's looking all right. So 3 or 5, well, those are 2 different numbers to pick from. Now, how many even numbers are there left to pick from? Well, I didn't pick an even number. So there's still all 5, 0, 2, 4, 6, and 8 to pick from. So there's 5 choices here. But now I have picked 2 numbers. Maybe I picked 3 and 8. There's still 8 numbers left to choose from here, and then 7 left to choose from for that spot, and then 6 left to choose from for that spot. And that's going to equal, I've now written it down over here, it's going to equal 3,360. So total, that's going to be what, 7,392 even numbers with distinct digits between 20,000 and 70,000. Again, kind of interesting, but who really cares, right? Question. Sure. So we want each digit to be different than the other one, right? So what I'm doing is, first I'm picking this number. And let's do this one here. So I picked 2, 4, or 6. Let's say I picked 4. And then I'm picking this number next. Well, that number has to be even. It can't be 4 because I already picked 4. So it can either be 0, 2, 6, or 8. There's 4 choices for that one. Let's say I picked 8. Now, since the digits have to be distinct, I've already picked 2 of the digits. There are 8 choices left for this spot. Let's say I pick 5. And there are 7 choices left for this pick. Let's say I picked the number 2. And there is 6 choices left for this spot. So I've already picked 4, 5, 2, and 8. I'm going to pick 1 for the last one. So that's one way I could pick those numbers in that order. But definitely, right, in this first spot, there's only 3 things to choose from. In this last spot, there are 4 things to choose from. And then in the third spot here, or I should say the second spot, right, there are 8 things, then 7 things, and 6 things to choose from because they have to be distinct.
Oh, when you put first digit 2, 4, 6, why don't you put like 2, 4, 6 in that first blank? Like you chose 3.
Well, sorry. So these are different things here. So this is 3 is the number of choices. So 3 possible choices, 4 possible choices, 8 possible choices, 7 possible choices, 6 possible choices. It's not that I'm picking the number 3. I was saying there's 3 things to pick. And then the same deal down here. Somebody else asked, where do you get the 8 numbers to choose from? So I think I answered that question already. I'll just say it again. Right? There's 8 choices here because I've already picked one thing here that had to be 2, 4, or 6, and one thing here that had to be an even number. Or here, one thing that was 3 or 5, and here, one thing that was 0, 2, 4, 8, or 6. Where am I getting these possible choices from? So from the problem at the beginning. So the problem says, how many even numbers are there between 20,000 and 70,000 with distinct digits? So to be even, it has to end with a 0, 2, 4, 6, or 8. To be between 20,000 and 70,000, it has to start with a 2, 3, 4, 5, or 6. So that's where I'm getting these choices from because of what the problem is limiting me to. Other questions?
Wait, I'm so confused. Like, if you're saying that the last question only has 0, 2, 4, 6, or 8, why is it 5?
So again, it's not the number 5. It's that there are 5 possibilities. 0, 2, 4, 6, or 8. The reason it's 4 here is because we already used one of those even numbers in the beginning spot. Right? That beginning spot was 2, 4, or 6. So I used up one of those even numbers. And then this one has whatever, it's 0, 2, 4, 6, or 8, except it can't be the one we've already picked over here. So maybe I picked 2. So I've got 1, 2, 3, 4 things left to choose from. So I want to be very clear though, right? These numbers here don't represent the number we picked. They represent the number of choices we have. So there are 3 choices. So in case 1, where the first digit is even, there are 3 choices for the first digit, 4 choices for the last digit, and then 8 choices, then 7 choices, then 6 choices for digits 2, 3, and 4. And when the first digit is odd, well, there's only 2 choices. It's either 3 or 5 because it has to start with 2, 3, 4, 5, or 6. So there's only 3 and 5 that are odd. 2 choices there times 5 choices for the last number because it could be any of the 5 even numbers. And then we pick 2 numbers. So there's 8 choices here times 7 choices there times 6 choices there. So I think that answers your question as well. Where are we getting these possible choices from? All right, let's do another one. Unless there are more questions, I'm really happy to answer questions. So, in fact, I'm going to have you guys do one. So, how many odd numbers are there? Between, let's say, 3,000 and 8,000 with, again, distinct digits. So you should think about 2 different cases. So I'll help you out. Case 1, the first digit is odd. Case 2, the first digit is even. In fact, I'm gonna help you out a little more. What possible choices do I have for my first digit? Could it be 1? No. Could it be 2? Could it be 3? Yeah. Could be 3 or 4 or 5, or am I going to be able to get to 8? No, right? 8,000 is not an option because 1 is even and 2, the digits are not distinct. So there are the choices for your first digit, 3, 4, 5, 6, or 7. I think you have no choices on the last spot. Less choices on the first spot. I agree there were 5 total odd numbers to pick from, but we limited the choice of our first digit because the number has to be between 3,000 and 8,000. I was on too. So it's really helpful to do this problem in the order of thinking about what the first digit can be, then what the last digit can be, then the second digit, then the third digit. So how many, in this case one where the first digit is odd, how many possible choices do I have for the first digit? 3. It could be 3, 5, or 7. So 3 choices. Not the number 3, 3 choices. Although it could be the number 3 because, okay. It's probably why the other example is better because the number doesn't match up with one of the possibilities. And then let's go to the last spot. So the last digit has to be 1, 3, 5, 7, or 9. So the last digit has to be odd if the whole number is odd. It can't be what we chose for the first digit because we chose an odd number already. So there are 4 choices. The last digit there. Yeah.
So for the first blank, what we choose has to be between 3 and 8, right?
Right. And specifically actually not 8. It's 3, 4, 5, 6, or 7. It can't be 8 because the only number that starts with 8 that's between 3,000 and 8,000 is 8,000. And it's neither, it's not odd and it also doesn't have distinct digits. So it's not going to be a possibility. And then we've chosen 1, 2 things. So there are 8 things left to choose from here. There are 7 things left to choose from here. I don't care what that multiplies out to. It's a number. We could do the multiplication on a calculator. Same deal down here. Well, similar deal. First choice we have, the first digit, we have 2 choices. It could be 4 or 6. Last digit, now we have 5 choices because it can be any of these 5 odd numbers that we didn't already pick one of. And then for the second digit, there are 8 choices. For the third digit, there are 7 choices. Do I mind explaining the choices again? Not at all. So, case 1, we had 3 choices because there are 3 numbers to choose from for the first digit. If our thing has to, well, sorry, I should say, case 1 where we're saying the first digit is odd, it can either start with a 3, a 5, or a 7 because the number has to be between 3,000 and 8,000. So it could be 3,000 something, 5,000 something, or 7,000 something. But it can't be 9,000 something. That's too big. Then the last choice, it has to end with an odd number as well if we want the entire number to be odd itself. We already picked an odd number in the beginning, so there's only 4 odd numbers left to choose from. Maybe I picked 5 in the beginning, and then it could either be 1, 3, 7, or 9 at the end. Or maybe I picked 7 at the beginning. It could be 1, 3, 5, or 9. Or maybe I picked 3 at the beginning. It could be 1, 5, 7, or 9. So already there's 12 different ways of picking a first number and a last number. I can even write them down, right? So I'm going to do that real quick to show you. The first number could be 3 blank blank, and the last number could be 1, 3 blank blank 5, 3 blank blank 7, 3 blank blank 9, or the first number could be, it's a lot of writing, 5 blank blank 1, 5 blank blank 3, 5 blank blank 7, 5 blank blank 9, or finally 7 blank blank 1, 7 blank blank 3, 7 blank blank 5, 7 blank blank 9. Those are the 12 ways the first digit can be odd and the last digit can be odd and then be distinct and the number be between 3,000 and 8,000. And then the middle 2 numbers can be anything. As long, well, it's 8 choices because I can't pick one of these 2 numbers here. I can't pick 3 or 1. I can't, in this one, I can't pick 3 or 5. Whichever one of these I'm looking at, there are 8 numbers left to choose from if I want them to be distinct. So there are 8 choices here. And then I've picked now 1, 2, 3 numbers. There are 7 left to choose from. there's 7 choices here. So there's 3 times 4, 12 times 8 times 7 choices altogether. And the same sort of thing is true here, right? I'm going to pick the first digit to be 4 or 6. So 4, and then blank, 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 blank. And then the last digit is odd, 1, 3, 5, 7, and 9. The same thing would be true if I pick 6 there. So there are 10 ways of having the first digit be even, 4 or 6, and the last digit be odd, 1, 3, 5, 7, and 9. And then there's still a good 56 choices for the middle numbers. Right? The middle numbers can literally be anything, as long as you haven't already used those numbers. So there's 8 choices for the first one, or I should say the second spot, 7 choices for the third spot. Sure, yeah. Oh, sure, yeah. It's easy to forget that 0 is a choice. So it's important. So this problem kind of avoids the issue, but typically 0 isn't a choice for the first digit, right? Which this one we don't really have to worry about at all. But right, if you're trying to come up with something, just remember usually we don't write 0 at the beginning of a number if you're doing a problem like this. If someone just said how many 5-digit numbers are there that are even, right? You wouldn't have a 5-digit number start with 0 because that's just a 4-digit number. All right. Why wouldn't 8 be a choice for the first digit again? Because if I pick 8, blank, 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 well, if I want to be between 3,000 and 8,000, my only choices for the other blanks are 0, 0, and 0. Otherwise, it's too big. But that doesn't meet the other requirements of the number, right? It has to be an odd number. Already, we're not in the right spot. And the digits have to be distinct. Already, again, we're not in the right spot. That's why 8,000. That's why 8 isn't a choice for the first number, because there aren't any possible results that have 8 as the first number. Okay. Let's change it up a little. Maybe if I can turn the page. Let's look at this. Suppose 5 girls and 4 boys are going to be seated on a bench. How many ways can they sit next to each other? How many ways can they be seated? Well, there are going to be many questions here. So let's look at the first possibility. If there are no restrictions, how many ways can we seat these 9 people? Well, excuse me, how many choices are there for the first seat? I guess I should ask, does order matter? Like if I was sitting the 9 of us in a row and I asked how many different ways could I do it, would it matter? Like if I grouped all 5 boys together, for example, there's still a lot of different ways I can do that, right? Me sitting first versus Jesus sitting first, right? It is a different permutation of the 9 of us. So there are 9 choices for the first person to sit in, say, the leftmost seat, and then 8 choices for the person to sit next to them, and then 7 choices, and then 6, and then 5, and then 4, and then 3, and then 2, and the last person sits over there. Well, there's no restriction. What I mean by no restriction is there's no restriction on where people have to sit. In the next question, we're going to make all the boys sit next to each other and all the girls sit next to each other. That's what I mean by restriction is there's some limiting kind of piece of information. So here, if there's no restrictions on where people can sit, we get kind of the most possibilities at all. Right? This is the 9 factorial is the most number of ways I could order these 9 people. No, I've exhausted every possibility. But now we want the girls to sit next to each other and the boys to sit next to each other. And the same for the boys. So either all the girls sit on the left and all the boys sit on the right. So the first 5 seats are for the girls. And the next 4 seats are for the boys. How many ways are there of doing this? Well, in seat one, how many choices are there? How many different people can sit in that seat? 5, right? There's 5 different girls that can sit in the seat. And then there's 4 girls, and then 3, and then 2, and 1. And same deal here. There's 4 choices for the boy that's in the leftmost seat, and then 3, and then 2, and then 1. So that would be 5 factorial times 4 factorial. But no one said the girls are the ones who had to sit on the left. So it could also be the case that we have boy, 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 and then girl, 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 girl. Which would also have 4 factorial times 5 factorial possibilities. And they're definitely different than those ones, right? All these possibilities have had a girl in the leftmost seat. All of these have a boy in the leftmost seat. They are definitely different. So altogether we have 2 times 5 factorial times 4 factorial possibilities. All right, what if instead we said we wanted just the boys to sit together? Well, I could either have all the boys on the left, like that. But I could also have something like this, where first there's a girl and then there's 4 boys. And then girl, 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 girl. Or I could have girl, girl, and then boy, 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 boy. How many different leftmost seats can the boys start at? Well, I can start here in the first seat, the second seat, the third seat. I mean, I guess I could write them all out, right? Girl, 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 boy, 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 girl, girl. Or those are the 6 different ways all the boys can be in like a different spot where they're still next to each other. Now, for each of these ways, how many ways can I order the boys? 4 factorial, right? There's 4 spots for the boys. There's 4 choices for the first boy spot, 3 for the next, 2 for the next, 1 for the next. And for the girls, the same thing. There are 5 factorial ways of seating the girls in these 5 seats. So in total, we're going to get 6 times 5 factorial times 4 factorial. Each of these, right, this has 5 factorial times 4 factorial possibilities. And so do each of these. So there's 1, 2, 3, 4, 5, 6 times 5 factorial times 4 factorial possibilities. Kind of a lot. Does that seem reasonable? What if instead I asked, how many ways are there that the girls sit together? All right, I'm gonna let you guys work on this one for a minute. But I want you to think about, you can either have girl, 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 boy, 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 boy. But the boys don't have to sit next to each other. So it could be boy, girl, 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 boy, boy, boy. So think about how many ways there are we could get that. And then each of these has 5 factorial times 4 factorial possibilities. Still, right? There's still, if you're putting the 5 girls in a specific spot, there are 5 factorial ways you can permute them. Second question. Yeah, there is a way you can, there's a, yes. So there's a question that I'll point out to you in a minute. This answer will be somewhat smaller than the previous answer. Not much smaller, exactly. Yeah, you guys got it. So somebody asked, I think it's a good question, is there a way we can do this without having to write out the sample space every time? And I wouldn't actually say that we're writing out the sample space necessarily, but I agree there is a way we could do this a little more efficiently. So instead of writing out all the different ways the 5 girls would sit together, you could ask yourself this question. If the 5 girls sit together, how many choices are there for their leftmost seat? Well, if the 5 girls have to sit together, the leftmost seat, the furthest right could be there, right? The first girl can't sit there. There won't be enough seats to the right. So there are 1, 2, 3, 4, 5 choices for the leftmost seat. Or essentially, there are 5 choose 1 choices. Sorry. For the leftmost seat for the girls. For the boys, there were 6 choose 1, right? If you look at the boys, there are 1, 2, 3, 4, 5, 6 possible first left seats. And so there were 6 choose 1 possibilities. So in this case, there are 5 choose 1 choices for the leftmost seat for the girls. And then after you've sat the 5 girls together, then there are 5 factorial ways of seating them. And then the 4 remaining seats, there are 4 factorial ways of seating all the boys. All right, let's ask one more question. How many ways can 2 specific boys sit next to each other? Well, let's call them boy 1 and boy 2. We want them to sit next to each other. So how many different spots could they be in? If boy 1 sits on the left, which doesn't have to, let's just pretend he is for a second. If boy 1 is sitting on the left, how many seats could he sit in? Can you sit in all 9 of them? No. Which seat can boy 1 not sit in? The last one, right? He can't sit over there if he's sitting on the left. So there are 8 choices for where boy 1 sits. Okay. And then boy 2 doesn't have a choice. He has to sit on the right side of boy 1. So we have 8 choices for where boy 1 and boy 2 sit. Times, well, it doesn't actually matter which one sits on the left and which one sits on the right. So I'm going to multiply those 8 choices by 2 because I could interchange where they sit. Right? They could switch seats and have a different arrangement. In fact, let's do that last. After I seat boy 1 and boy 2, everyone else can sit wherever they want. Right? The only requirement is that these 2 people sit together. Maybe they're brothers and they have to sit next to each other because they really love each other so much. Brothers should. I'm gonna see my brothers this weekend. I love my brothers. It's been a while. So anyway, well, I see one. I'm gonna see one of them anyway. The other one, we'll see if he shows up. He's got a new girlfriend. You know how it is. You're like, I don't want to go visit my family when I can hang out with my girlfriend. So anyway, back to math. Me and my brother sit next to each other in one of these 8 spots. And then everyone else can sit wherever they want. This is a good Thanksgiving. I should have made this more Thanksgiving theme. Oh, well, next question. Totally. There are 7 factorial choices for the Nelson. But then maybe my brother and I want to switch spots. We're still sitting next to each other. We've still met the requirements, but it's now a different permutation. So we have to multiply by 2 factorial. because there's two factorial, right? Two factorial. There's two factorial ways we could actually sit next to each other. So this would be the total number of ways that two specific people could sit next to each other at this bench that seats 9. Now, things get more interesting if you're sitting at a round table. And actually, that's literally actually the next question. I'm not just making this up. Like this is actually where we were going next. So how many ways? It is. Yeah, exactly. How many ways can 5 boys and 3 girls be seated around a table, meaning a circular table, if there are no restrictions? Well, you might think incorrectly that the answer is 8 factorial. Now, I should clarify a little bit. Technically, if everyone sits in a spot and then we rotate, like everyone moves like 2 seats to the left, technically you could argue that's a different orientation, right? Because you're in a different spot in the room, you're looking at different stuff. But if we're just concerned about who's sitting next to who, then it doesn't matter if the 8 of us are sitting here, or if we all move 3 seats to the left and the 8 of us are sitting here, right? Still, I'm sitting still next to the same 2 people, and so is everyone else. Meaning that, well, basically you have to fix someone. Right? Someone goes in one spot. So let's say at this table of 8 people, we're going to fix James there. I get to sit there. And then the other 7 spots, there are going to be, no one wants to sit next to me, sorry. There are going to be 7 factorial choices. Or I should say, really 7 factorial permutations. But it's not going to be 8 factorial. Because, right, 8 factorial would then account for me sitting in any one of these other spots, but then still with the same orientation as the other 7 people around me in the same way. So when you're seating people at a table, more generally, there are n minus 1 factorial ways of seating n people at a table. All right, well, let's throw in some restrictions. Let's say that now my brother and I don't want to sit next to each other. So James and Michael will not sit next to each other. And then their mom says, you must. No. Okay, so how do we deal with that? Well, again, typically when you're at a round table, you really want to fix someone. So you want to say, well, let's say James has to be at that seat there. And then there's still 1, 2, 3, 4, 5, 6, 7 other seats to sit at. Who should I seat next? Well, who's the only other person we've talked about? My brother Michael. How many choices does Michael have to sit at? Show me on your fingers. You only need 1 hand. You do need all the fingers under 1 hand, though. He has 5 choices, right? Because he's not going to sit here next to his older brother or here next to his older brother. He's going to sit in one of those 5 spots there. So there are 5 choices for Michael. And then everyone else can sit wherever. So how many seats are left? Not 4, but 6. Because there's the 4 spots Michael also could have picked. Maybe he sat there. And there's also the 2 spots next to me that he didn't want to sit in. So there are 6 factorial choices for the other 6 people who are sitting at this table. Okay? Which is, I don't know, but doesn't really matter. But now I'm like, it's 600. No, that's wrong. I'm off by a factor of 6. It's 3,600. Doesn't really matter. What if instead none of the girls want to sit to each other? I mean, that happens, right? Happens with boys too. Like, no, I don't sit next to boys. Now, if we said none of the boys sit next to each other, that'd be a problem because there are 5 boys and 8 seats. It wouldn't be possible, right? Okay, so how are we going to do that? Oh, interesting. So, sorry, I'm just looking at the way this. I think someone wrote this question thinking that there were 10 seats at the table, which seems wrong, right? Because they're not the way I framed it anyway. Apologies, 1 second. No. Okay. How are you seeing these? So here's our table of 8. I'm going to say 8 chairs. So let's say we see the boy here. Now, I feel like this question is not good. I'm gonna pass on this question because I feel like I think there's something else here that might be. But now I'm like really want to answer it. Oh, fine. We can figure this out. I changed my mind. It seems like now I'm like, this question seems hard. Okay, well, that's interesting. So how many ways can we sit so that the 3 girls are not adjacent? Okay, whoops, you want to see that. So here's the way I'm going to think about it. Let's seat 1 girl. All right, so there's 7 seats left. I think we have to do this in a couple of different cases. How many choices does the next girl have for a seat? Well, same thing with me and my brother not sitting next to each other, right? I sat there, and then my brother couldn't sit here or here. There were 5 choices left. So girl 1 sits down. Girl 2 has 5 choices. Now, this is where I think things are going to get a little bit dicey. So let's say she picked to sit. So let's say she picked seat 2. If she picks seat 2, red, how many choices does girl 3 have? It looks like 1, 2, 3. So if girl 2 is in seat 2, girl 3 has 3 choices. Is that going to be the same no matter what seat she picks? I don't think so. Let's see if she picks seat 3. So she picks seat 3. Yeah, then girl 2 can't sit in seat 1 or 2. So she can either sit in seat 6 or 7. So there she has 2 choices. Interesting. It seems like a complicated question. And then I think any other seat is fine. So yeah, so if girl 2 is in seat 2, girl 2 is in seat 3, I guess we should look at the rest. So girl 2 is in seat 4. Yeah, then girl 3 can be anywhere because she can be in 2, 4, 6, or 7. Yeah. So then there's 3 in seat 5. There's also 3. Ooh, no. In seat 5, there's only 1, 2 possibilities, right? Because in seat 5, she can't sit in seat 6 or 7, or seat 1, yeah, or 4. There's only 3 and 2. Interesting. So in seat 5, there are 2 choices. And in seat 6, there are 3 choices. That's kind of complicated. I'm not gonna I feel like this would be a too hard question in a lot of respects for myself, and like this is okay. So I think we can write it out now. So girl 1 sits down. Girl 2 has, we have to add these together. So girl 2 has either, oh, girl 2 has 5 choices, but really, oh, okay, let's do it this way. So in 1, 2, 3 of her choices, girl 3 also has 3 choices. Girl 2 has 3, girl 3 also has 3, and then the other 5 boys can sit wherever. So there's 5 factorial ways of doing that. Or 2 of the spots girl 2 could pick. Girl 3 only has 2 choices. But then the other 5 boys can still sit wherever the heck they want. So this would be 9, that would be 4. We're going to get 13 times 5 factorial choices. Oh, there's probably a better way I could have done this. That's all right, though. You guys want to see the better way? I think you do. I think that, so now I'm like, yeah. Now I'm really like curious. So, oh yeah, there's a better way. So girl 1 sits here. Nobody sits next to her. No girl sits next to her. There are 5 seats left to choose. Oh, yeah, okay. So in these 5 seats, yeah, okay. Sorry, I'm really like, now like this question's kind of cool. Okay, so here's what we got. Let's do it one more time. I know you guys are like games, but Thanksgiving's a hard time, you know? Gotta figure out where everyone's sitting. None of the girls want to sit next to you. It's a big problem. 2, 4, 6, 8. Okay. So here's where girl 1 sits. These seats are out. How many choices? So there's 5 seats left that the other 2 girls can sit in, right? So 2 people sitting in 5 seats, there are 5 choose 2 ways they can do that. Now, I know that's too many possibilities. Don't worry, we're going to eliminate some of them. So there's 5 choose 2, which is, you know, like the way I counted it before wasn't right. So sometimes you count something and you think you're right and you're wrong. Oh, I double counted. Did I double count? So we're going to need to write them all out. Okay, so here's what I'm seeing. You can have girl 2 and girl 3, or yeah, let's just do this. Let's do that. So in seats 1, 2, 3, 4, 5, you can have 1 and 2, or 1 and 2, or 1 and 2, or 2 and 4, or 3 and 5, or 3 and 1. How interesting. Huh. But then you can also switch them, right? Because maybe girl 2 sits here and girl 3 sits here and girl 2 sits here. So you can also do, so there's, sorry, my brain's like, this is super cool. 3, 4, 5, 6. How did I overcount before? All right, I think we've talked about, so I feel like I'm not going to get to the answer for you guys very definitively. And more importantly, it's not that important. And I'm like, this is super cool, but I could also not waste your time for the next 20 minutes doing this. So let's move on. I'm going to work on this later because I won't be able to stop myself. And I'll post something up just just for your satisfaction, so I can be like, that's how we actually got this work. But yeah, I'm going to have to think about that. There's a number of ways you can probably try to tackle it. Enough people sitting next to you. Let's talk about cards. Another important part of Thanksgiving. Playing some cards. So most of the time, not all the time, but most of the time when people talk about cards, they usually talk about it in the context of poker. So you should be familiar with the poker hands. Let's first ask ourselves, how many different ways could you get a pair? All right. Well, so, and I should say, when we say how many different ways could you get a pair, we mean a pair out of the 5 cards that are going to be dealt to you, because that is the standard amount of cards typically in a poker game. At least it's the amount of cards you get to play. Some games you get 7 cards, like 7-card stud or Texas Hold'em, but even if you have 7 cards to choose from, you only get to play your best 5. So, when I'm thinking about this, I'm thinking about, well, how many different pairs could I get? Well, I can get a pair of aces, or 2s, or 3s, or 4s, or 5, 6, 7, 8, 9, 10, Jack, Queen, King. How many different ranks of cards are there? 13. How many different suits are there? 4. Right, there's 13 ranks, there's 4 suits, 13 is 4, 52 cards in a deck, which is twice as many letters as there are in the alphabet. I know it's not important, but it's sometimes it comes up that there's 26 cards in half a deck, there's 26 letters in the alphabet. Sometimes it's a nice fact to be aware of. So there are 13 choose one choices for what rank I'm going to have. Pair of aces or pair of 8s? Well, let's say it was 8s. How many different ways could I have 2 8s in my hand? Well, how many different there's 4 different 8s to pick from. So there are actually 6 different ways I could have a pair of 8s. I could have the ace of aces, ace of 8, 8 of spades and diamonds, or spades and clubs, or spades and hearts, or diamonds and hearts, diamonds and clubs, or clubs and whatever the last one is. 4 choose 2, which is 6. But that's not all. I've only chosen 2 of the cards. There's still 3 cards left to choose. And I want those 3 cards to be not the same as each other, because then I will have, maybe 2 pair. And I don't want 2 pair. I want just 1 pair. And also not the same as this rank I already picked. So of the 12 remaining ranks that are not 8s, I want to choose 3 of them, 3 distinct ones. And then from each of those ranks, so let's say, right, we've chosen 8s, and there are 2 of them. And now we're choosing 3 other ranks that are distinct, say kings, jacks, and 2s. And I want 1 of each of those. Well, there are 4 choose 1 kings to choose from, or I should say there's 4 kings to choose from. We're going to choose 1. There's 4 jacks to choose from. We're going to choose 1. There's 4 choose to choose from. There's 4 2 to choose from. That's how, say that again fast. There's 4 choose to choose from. I'm going to choose 1. Be careful. It's really easy to make the mistake of doing this. That's an 11, sorry. This is not the same. So here, the difference between what I've written here and I've written here is here what we've done is we've chosen the 8s first and then picked 2 of them. And then we've chosen 3 different ranks, kings, jacks, and 2s, and then picked 1 of each of them. Where you're picking the kings, jacks, and 2s all at the same time. Meaning we don't care what order we get our king, jack, and our 2 in. Doesn't matter if you get the king dealt first, the 2 dealt next, or the jack dealt next, or some other permutation of that. Whereas here, this differentiates between 2 8s and a jack, king, and a 2 versus 2 8s and a king, jack, and a 2. This way I'm multiplying it out counts those differently. Because here, right, if I have 12 choices here, I could pick a jack first, or I could pick a king first, and those are getting counted differently. Whereas here, that's not the case. So the real difference here is that the 12 choose 3 part, remember 12 choose 3 is 12 factorial over 9 factorial times 3 factorial. Whereas the 12 choose 1 times 11 choose 1 times 10 choose 1. What is 12 choose 1 again? Just everybody remind me that you know what 12 choose 1 is. Please. It's 12. Right? 12 choose 1 is 12. There's 12 ways of choosing one thing out of 12 things. So these things multiplied together are 12 times 11 times 10, which is 12 factorial over 9 factorial. And the difference between these two is that this is counting the 3 factorial permutations of those jack, king, and 2 as different. Whereas this is not. This is dividing by that 3 factorial so that we don't count those as different.
Is that second box a 14 or?
That's an 11. I know. It looked like a 4 at first. Sorry. That is 11. Choose 1. Good question. It looks like trash. Sorry. It looks like an H choose 1. Really is what it looks like. But no, that's 11 choose 1. So yeah. So the difference between this and this is that this doesn't care what order the king, jack, and 2 come in, which we shouldn't. Right? When we get 5 cards, we don't care what order we got them dealt in. Not in poker anyway. Whereas here, this is counting a jack, king, 2 differently than a king, jack, 2. And we don't want to do that. All right. So it can be a little weird. Questions about this? Yeah.
Where is the 4 choose 1?
So the 4 choose 1 is that after I've decided I want jacks, kings, and 2s, there's 4 jacks to pick from. Hearts, diamonds, spades, and clubs. There's 4 kings to pick from. There's 4 2s to pick from. So whenever you're picking some number of a particular rank, you have to say, well, if I want one of them, there are 4 different suits I can pick. Or if I want 2 of them, there's 4 choose 2, which is 6 ways of picking 2 of the 4 of them. If I wanted 3 of them, it's 4 choose 3, which is also 4. But there's 4 ways of picking 3 of one kind. Or there's 4 ways of picking not one of the 4 of the cards I want. Let's look at a different example. Yeah, we got a little bit of time. Let's say how about 2 pairs? And we're gonna contrast this with a very interesting question. So 2 pairs, well, again, the same kind of deal. So let's talk about how to pick the pairs. There are 13 ranks. So let me ask, do I want to do this? 13 choose 2, or do I want to do this? 13 choose 1 times 12 choose 1 to pick my ranks. So here's what this would be doing. I did 13 choose 2. It would be counting, say, ace, ace, and jack, jack, the same as jack, jack, and ace, ace. Whereas here I'm saying, well, first I'm picking one rank, let's say aces, then I'm picking the second rank, let's say jacks. That'd be different than doing jacks first, aces second. I don't want them to be different. So if I'm picking 2 pair, it doesn't matter which pair I get first. It doesn't matter which rank I decide first. I don't want this. Question? Okay, stretching. All right, so I've picked my ranks, aces and jacks. And then there's also going to be another card that is neither of those. Right? If you want 2 pair, you want 2 pairs of cards, and the 5th card shouldn't be the same as either. Otherwise, you have a full house, which is a totally better hand. So we're going to have 13 choose 2 ranks times, leave myself some space there, 11 choose 1 ranks. right? We picked aces and jacks, and then there's 11 other types of cards to pick from. 2, 3, 4, 5, 6, 7, 8, 9, 10, queen or king. All right, for each of my pairs, I didn't leave myself enough room. That's all right. For each of my pairs, how many ways are there of choosing 2 jacks? How many ways? Well, there's 4 jacks to choose from. I'm choosing 2 of them. Kind of already said the answer. It's 4 choose 2. And there's also 4 choose 2 ways of choosing 2 of the other thing. Aces in this case. Which I didn't leave myself space for. So that's the number, the 2 different ranks. That's the number of ways to pick 2 whatever's aces. That's the number of ways to pick 2 jacks. Now, at this point, you could say, all right, if I pick 2 aces and 2 jacks, how many cards are left in the deck to pick from? If I don't want to pick another ace or another jack. Well, how many cards are in the deck total? 52. And I said there's 8 cards I don't want. I don't want any of the 4 jacks. I don't want any of the 4 aces. How many cards are left? 44. So you could just say at this point, well, there's 44 choices for the last card, which would be totally fine. But the more systematic way of doing it, saying there's 11 choose 1 choices for the rank. And then after you pick your rank, there's 4 choose 1 choices for the suit. But that's exactly 11 times 4, which is 44. So sometimes if you like, there's only 1 card left to pick from, you can just ask yourself, how many cards can I pick out of? Oh, there's 44 cards I want to pick from. I don't want to pick any of the aces or jacks, but any other card is fair game. All right. Now, there's an interesting contrast here. Interesting, maybe in quotes. What if instead we did want to get a full house? Sorry, there's not enough room on the page for everything. So, in case you didn't know, a full house is a hand that consists of 3 of one kind and 2 of another kind. So, like 3 aces and 2 sevens, or 3 8s and 2 5s. So, how many different ranks am I choosing? Well, there's 5 cards. 3 of them have to be one thing. 2 of them have to be another thing. How many different things am I choosing? 2. They're right. I'm choosing 8s and 5s, or aces and jacks, or whatever's and whatever's. So that's all the cards in the hand. 3 of one thing, 2 of another thing. So there's 1 thing here, 1 thing there. Now, here is the thing that's maybe a little confusing. We're not going to do this as 13 choose 2. And here's why. 13 choose 2 would tell you all the ways you get 1 rank and another rank. So you have 13 choices for your first rank times 12 choices for your second rank, but then you don't care what order they're in when you do 13 choose 2, right? That's 13 times 12 divided by 2. The problem is we do care what order they're in. The reason we care about the order, well, it's really so much, we care about which one is the 3 of the kind and which one is the 2 of the kind. Right? It actually matters. 3 aces and 2 5s is different than 3 5s and 2 aces. And one of them is a better hand than the other one. So in this case, we actually do have to pick the rank separately. Say, well, I'm going to pick 1 suit for my 3 of a kind. Sorry, 1 rank, apologize. 1 rank for my 3 of a kind. And then I'm going to pick 3 of those 4 cards. So 4 choose 3 ways of getting that 3 of a kind. I could have 3 aces and I don't want 1 of the suits. And then from the remaining 12 ranks, I'm going to choose 1 of them to be my 2 of a kind. I've definitely seen teachers mess this up when they teach it. Right? In fact, there's one professor who we've talked to a few times about how doing it this way is actually incorrect because you're undercounting. Yeah, you're undercounting how many answers there actually are. So, and then for my 2 of a kind, whatever rank I pick of the 4 different suits, I want to choose 2 of them. And that's how many full houses there are, which would be, you can actually calculate this pretty easily. It's 13 times 4 times 12 times 4 choose 2 is 6. Whatever number that is. He said easily, not that easily. Sure, a full house is just a hand of 5 cards where you have 3 of one kind and 2 of another kind. So like 3 aces and 2 sevens, or 3 5s and 2 8s. So this is different than not 13 choose 2 times 4 choose 3 times 4 choose 2. Because this calculation here doesn't differentiate between which is the 3 of the kind and which is the 2 of the kind. So it actually undercounts. Kind of interesting. It's also a very kind of subtle detail there. All right, let's do one more and then we will call it a day. How about a flush? How many ways of getting a flush? Well, this is a terrible question. And here, I'm going to show you why it's a terrible question. It's not actually that terrible, but I'm going to show you why it's a little terrible. So a flush means all the cards are the same suit. So first of all, let's pick a suit. How many suits are there to pick from? 4. So the 4 suits, we're going to choose 1. All right. How many cards are in that suit? 13. Of the 13 cards in the suit, how many do we want? How many go in our hand every time? 5. So we're going to pick 13, choose 5. And that's going to be our answer. Well, it's actually not. So here's the deal. If you were actually playing poker and someone said they had a flush, that would be the best hand they could possibly have, right? You're never going to say you have a lesser hand than you have. You want to win the money. So the problem is some flushes are straight flushes, right? If you have a 2, 3, 4, 5, 6 of hearts, that's not just a flush, that's a straight flush, and that's a much better hand. So if someone says they have a flush, they don't actually have a straight flush. So we don't want to count those straight flushes. So how many straight flushes are there? Well, we're still going to pick a suit. But now here's the thing for a straight flush. You have to pick a starting card for the straight. So what's the lowest starting card you can pick? Where's the lowest the straight can be? Ooh, interesting. Yeah. So this is going to be, this is a good question. So a straight can start in an ace. Right? You can have ace, 2, 3, 4, 5. What's the highest, lowest card a straight can start at? It's 10, because you can have 10, jack, queen, king, ace. And ace can count high or low. So for each suit, there are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10 different straight flushes. Ace, 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. You get the idea, all the way up to 9, 10, jack, queen, king, and then 10, jack, queen, king, ace. So there are 10 choose 1 starting places. So there are 40 straight flushes, which means that the number of actual flushes that are not straight flushes is really that number, 4 choose 1 times 13 choose 5 minus 4 choose 1 times 10 choose 1. That would be the number of true flushes that are not also straight flushes. Again, probably not a super important detail, but it's important when you're playing poker. So yeah, that's all I got to say about that. Next week, we meet on Tuesday, I think we'll talk about probability actually. So I will just prime you with the fact that when we talk about probability, we're just talking about the number of ways. So I said, what's the probability of getting a flush? It would be the number of ways of getting a flush, which we just counted, divided by the total number of possible poker hands, which is 52, choose 5. There's 52 cards to pick from, there's 5 cards to pick. So in general, probability is the number of ways of getting the thing you want, divided by the number of ways of getting anything. Somebody asked, in the rules of poker, the queen and king are not included. The queen and king are included. So for a flush, I'm picking the suit. There's 4 different suits to pick from, and then there's 13 cards, which includes the king and the queen and the jack and the ace, and we're picking 5 of them. So a flush could be, for example, 2 of hearts, 3 of hearts, 7 of hearts, 9 of hearts, king of hearts. That would be a flush. A straight flush would be, for example, 2, 3, 4, 5, 6 of spades, or 8, 9, 10, jack, queen of diamonds. Those would both be straight flushes. But a flush or a straight flush can definitely include any of the face cards.